Welcome everybody to my presentation, an online calculator for qubits based on geometric algebra. My name is Dietmar Hildenbrand from the University of Technology in Darmstadt. And this is joint work with Christian Steinmetz, Rafael Alves, Jaroslav Dina, and Khalil Lavor. That's a summary of my presentation. First of all, I would like to talk about quantum computing in general, explaining what quantum bits, quantum registers are, and present one operation on a qubit as an example, the NOT operation. After that, I would like to answer the question why geometric algebra is so interesting for quantum computing, and then present our contribution. First of all, the specific qubit algebra, and then our solution for handling these kind of calculations online via Gallup Web. And as an extension, I will present the two-qubit algebra as a more generalized algebra for quantum registers, and present also Gallup Web for an example on two qubits. Classical bits have either the value of 0 or 1, but the difference to quantum bits is that these kind of bits can have all the values between 0 and 1 also. This is called superposition, and the state of a quantum bit can be described as the sum A0 times state 0 plus A1 times state 1. A0 and A1 are the coefficients, and these are complex numbers in quantum computing. A0 square plus A1 square equals to 1, and the meaning of A0 square and A1 square, these are the probabilities for either the state 0 or the state 1. A quantum register is in principle a sequence of quantum bits. Quantum registers can also be described based on the superposition. In the case of two qubits, it is a combination of the four basic states 0, 0, 0, 1, 1, 0, and 1, 1. And again, the coefficients A00, A01, A10, and A11 are complex numbers. Again, their sum of the squares equals to 1, and the square of the coefficients describe the probabilities for each state. Let's come to an operation on a single qubit. The NOT operation is a very simple operation on a qubit. Physically, it means that both states 0 and 1 have to be mapped on each other, means the state 0 to state 1 and the state 1 to the state 0. Algebraically, it can be described based on the coefficients of the superposition formula, means the two probability amplitudes A0 and A1 have simply be interchanged, means A0 is mapped to A1 and A1 is mapped to A0. And what about the geometric point of view? In order to realize the NOT operation, having the two states for 1 and 0, here they are the sigma 1 and the sigma 0. Um, the meaning is to reflect about a reflection vector as the bivector between these two basis vectors and normalize it. This is what this formula means. This can be seen in more detail at the figure of this slide. In this figure, we see sigma 0 and sigma 1 as coordinate axes describing the basic states 0 and 1. And the application of the not operation on one state vector geometrically means the reflection at the bisector between these two coordinate axes, which can be described with the formula of RF as shown on this slide. And since the operations on qubits always have some kind of geometric meaning, um, this can be easily be described based on geometric algebra. This is already one answer to the question why geometric algebra is so interesting for quantum computing. It means operations or gates, as they are normally called in quantum computing, can be expressed very intuitively with geometric algebra. This is one advantage, and the second very important advantage is that qubits and operations are elements of the same algebra. And this is already used in many papers. For instance, the papers of Alves and Lava, of Baylis, of Cafaro and Mancini, also Christoren and Anthony Lazenby in their book from 2003 describe quantum computing based on geometric algebra, and also in the paper of Vienna from 2008, there is a focus on this big advantage of geometric algebra for quantum computing. Let's come now to the geometric algebra we propose for quantum computing. It is called qubit algebra, or QPA for short. This algebra consists of 4 basis vectors, 2 for every quantum state, and with positive and negative signatures. Um, means this algebra is inspired by space-time algebra with these different signatures of 1 and -1. Means the state 1 consists of 2 basis vectors. One is space-like, one is time-like. They are called gamma 0x and gamma 0t. And the same for the state 1. Also space-like, time-like components, means consisting of the basis vector gamma 1x and gamma 1t. And in Gallop script, the description of these basis vectors is E0x, E0t, E1x, and E1t, since in Gallop script all the basis vectors have to start with an E. In order to calculate with QPA, we extended our online tool Gallop Web. In principle, Gallop Web takes a geometric algebra algorithm and generates optimized code for different programming language. In the case of QPA, we extended this tool in order to take a QPA algorithm and generate code for instance, C++, Python, MATLAB, Mathematica, Ganja, Julia, Rust, or LaTeX. This shows the screen for Gallop Web for qubits. What we can see at the top of the screen is that quantum bits GA is selected and the number of qubits is 1, since our NOT operation only needs 1 qubit, 1 is enough. Then let's look at the algorithm for the NOT operation described in Gallop script. In line 1, the state vector R is described based on the superposition of the 4 basis vectors. Then 2 reflections are computed, one between E0x and E1x, and one between E0t and E1t. Then both are multiplied, and then the transformation of the state R to R prime is computed in line 5, and the question mark in Gallop script means that this line has to be evaluated explicitly, means in this algorithm we are only interested in the value of R prime. Okay, and this screen now shows the C code for the NOT operation, and in principle it computes as a C function the multivector R prime. At the end of each line we can see the components, means R prime is linear combination of the basis vectors E0x, E1x, E0t, and E12t, the same as our original multivector R. But what we can see is that the space-like and the time-like components are always interchanged. Means R is a linear combination of C0x, C1x, C0t, and C1t, and the C1x, C0x are interchanged, and the C1t and the C0t are interchanged. Means the result shows us that exactly the coefficients that have to be interchanged are now interchanged. Okay, this was done in the QBA for 1 qubit, and let's come now to the 2-qubit algebra QBA2. This algebra consists of 8 basis vectors for the states 0, 0, 0, 1, 1, 0, and 1, 1. Again, all the states have a space-like and a time-like component with the different signatures, and in Gallop script these basis vectors are described with E0x, E0t, E1x, E1t, as well as E2x, E2t, E3x, and E3t for the 4 states. This is a screen for Gallop for 2 qubits. What we can see is that the number of qubits now is set to 2, and we again use the NOT operation as an example for that, And since we now have 2 qubits, the NOT operation has to be applied on both qubits. For that, we defined the NOT operation as a macro in Gallop script, means the algorithm is the same as before, but now we need some parameters underscore p1, underscore p2, underscore p3, and underscore p4. And then we define the state vectors r1 and r2 based on the corresponding basis vectors for these qubits, and compute the NOT operation on that, and evaluate r prime 1 as well as r prime 2, since both are equipped with a question mark. This is the result of the operation of applying the NOT operation on 2 qubits on a register consisting of 2 qubits. In principle, we compute the components for the multivectors r prime 1 and r prime 2. And if we look in detail on these components, we again can see that the space-like and the time-like components are interchanged. As a conclusion, we could see that qubits and operations are both elements of QPA, and that operations can be expressed intuitively with this QPA. And additionally, with Gallop Web, we are able to calculate with QPA in a very easy way via code snippets of this online application. These are all the references of our paper. They include the already mentioned publications, as well as, for instance, number 5, my book, Introduction to Geometric Algebra Computing, as an introduction to this technology, as well as some additional papers and books describing quantum computing in general. Thank you very much for your attention. And now it's time for 10 minutes of questions. Thank you.